All right, ready to dive into some A-level physics? Specifically, we're tackling electricity today from the AQA syllabus.
Sounds good.
It can be a tough topic, all those equations and theories. Hopefully we can make it a little more clear today.
Absolutely. That's the goal. We'll try to break it down and explain things in a way that makes sense.
Perfect. So let's start with the basics. What actually is electricity?
Well, think of it this way. Imagine water flowing through a pipe.
Okay, I'm picturing that.
Good. The water, in this case, represents the electric charge, and the pipe is like the wire.
Okay, so the flow of that charge is what we call the electric current, right?
That's right. And like water needs pressure to flow, electric charge needs something to push it along.
So what's the electrical version of water pressure then?
We call that potential difference, or voltage for short. It's basically the driving force that pushes those charges through the circuit.
Okay, I think I'm following so far. Higher voltage, more push, more current. Makes sense.
Exactly. But there's another factor to consider: resistance.
Resistance. Like something slowing down the flow.
Precisely. Think of it as bumps inside that water pipe, making it harder for the water to flow smoothly. Resistance is the measure of how much a material or component opposes the flow of electric current.
So current, voltage, and resistance are the key players here.
You got it. And each component in a circuit interacts with these players in its own unique way.
Okay, like what? Give me an example.
Well, take a resistor, for example. You might remember Ohm's law from your A-level.
VIR, right.
That's the one. It means the voltage across a resistor is proportional to the current flowing through it.
Okay, so if you increase the voltage, the current increases proportionally.
Exactly, a nice linear relationship. But not all components behave so predictably.
I was just thinking about that. What about diodes? They're kind of strange.
They are interesting, aren't they? They only allow current to flow in one direction, like a one-way street for electricity.
I'm picturing like a valve or something that only opens one way.
That's a great analogy, and they have all sorts of uses because of this unique behavior.
Okay, diodes, one-way street. What else is there?
Well, how about something you've probably seen burn out a few times? Filament lamps.
Oh yeah, those old school light bulbs. Why do they always burn out right when you turn them on?
Good question. It has to do with the way their resistance changes with temperature. As the filament heats up, its resistance increases.
So more resistance means more heat.
You got it. And that initial surge of current when you flip the switch can be enough to cause the filament to overheat and, well, burn out.
It's like a delicate balance, isn't it? All these factors playing together.
It is. And it's important to remember that all this happens in real-world scenarios, not just in a perfect textbook world.
Right. Things are always a bit messier in reality. Like even the tools we use to measure electricity, they have their limitations too.
Absolutely. Ammeters and voltmeters are useful, but even they aren't perfect. It's something to keep in mind when analyzing real-world circuits.
Speaking of the real world, why do some materials conduct electricity so much better than others?
That comes down to a property called resistivity. It's basically a measure of how strongly a material resists the flow of current.
So a material with low resistivity is a good conductor.
Precisely. Think copper or aluminum. Those are classic examples. Materials with high resistivity are good insulators, like rubber or glass.
Makes sense. So it's all about how easily those charges can move through the material.
Exactly. And things get even more interesting when you start factoring in temperature, right? Temperature can really shake things up.
I can imagine. It's like how things move faster when they're hot, right?
Mm.
Does that apply to electrons too?
It does in a way. See, in most metals, when the temperature goes up, those atoms start vibrating more.
Okay.
And all that shaking makes it harder for the electrons to flow smoothly, so the resistance increases.
Oh, I see. So like if you heat up a wire, it becomes less effective at conducting electricity.
Exactly, which is why things like your phone charger can get warm when you're using them. Some energy is lost as heat because of that resistance.
That makes sense. But wait a minute, don't some materials do the opposite? Doesn't their resistance go down when they heat up?
You're thinking of thermistors. They're pretty special. As the temperature rises, they actually release more charge carriers, making it easier for current to flow.
Oh, wow, that's cool. So they kind of have a built-in thermometer almost?
You could say that, and that's why they're often used in temperature sensors, like in thermostats or even in your car engine.
Wow, that's pretty neat. Okay, so we've got conductors, insulators, things that get more resistant when hot, things that get less resistant when hot. Is there anything else out there? Any other weird electrical behaviors?
Well, how about zero resistance?
Zero. Is that even possible?
It is. Well, under certain conditions at least. We call those materials superconductors.
Superconductors, that sounds intense.
They are pretty amazing. Below a certain critical temperature, their resistance completely vanishes. The current can flow without any loss of energy.
No energy loss. That's incredible. What could you even do with that?
All sorts of things. Lossless power transmission would be huge, and incredibly powerful magnets for things like maglev trains or medical imaging. The possibilities are pretty mind-blowing.
It sounds like something straight out of science fiction.
It does, doesn't it? But it's real science. And who knows what the future holds for superconductors? It's an exciting area of research.
Well, I'm definitely intrigued. So we've covered a lot of ground with these individual components and materials, but how do they all work together? What about circuits?
Circuits, that's where the real fun begins. They're like the roadmaps for electricity. They dictate how the current flows through the various components.
Okay, makes sense. So like series and parallel circuits, those were always a bit confusing.
Don't worry, we'll break it down. Think of a series circuit like a single lane road.
Okay, got it. One lane.
The components are connected one after another, and the current has to flow through each one in turn.
So if one component slows down the flow, it affects the whole circuit.
Exactly. It's like a traffic jam for electrons. And the total voltage supplied by the battery is divided up among the components.
I see. So each component gets to share the voltage, and the current is the same throughout.
You got it. Now, parallel circuits are a bit different. Imagine a multi-lane highway now.
Multi-lane. Okay. So more options for the current to flow.
Precisely. The components are connected in parallel, creating multiple paths for the current to take.
So it's like the current can choose which way to go.
In a way, yes. It's always going to take the path of least resistance.
Okay. So in a parallel circuit, each branch gets the full voltage, but the current is split between the branches.
Exactly. And calculating the total resistance in a parallel circuit is a bit trickier than in a series circuit. It involves using the reciprocals of the individual resistances.
I vaguely remember that from my A-levels.
Yeah.
Definitely a bit more complex than just adding them up like in a series circuit.
It is. But understanding how series and parallel circuits work is crucial for understanding more complex electrical systems.
Right. It's all building up to a bigger picture. Okay. So we've talked about circuits, components, materials. But what about energy? My parents were always on my case about wasting electricity, but how does that tie into all this?
Energy is the key. When we talk about power in an electrical circuit, we're talking about the rate at which energy is transferred.
So like watts
Yeah.
on a light bulb or something.
Exactly. A 100-watt bulb is using 100 joules of energy every second. And power is directly related to both current and voltage. Remember those equations, PIV, PVR, RPIR?
Oh, yeah, those bring back memories. So understanding power helps us understand how much energy a device is using.
Precisely. And it also leads into the idea of energy efficiency. Just because a device has a high power rating doesn't mean it's using that energy effectively.
Right. A device could be using a lot of power, but wasting most of it as heat, for example.
Exactly. So understanding these concepts helps you make smarter choices about the technology you use. You can choose more energy-efficient devices and reduce your energy consumption.
I like that, being a more informed consumer. So we've covered current, voltage, resistance, circuits, power. Is there anything else we need to know to master the world of electricity?
Well, how about controlling that flow of electricity a bit more precisely? Have you ever wondered how a circuit can provide just the right amount of voltage to a specific component?
Now that you mention it, yeah. Like how does my phone charger know exactly how much voltage my phone battery needs?
That's where potential dividers come in. There are circuits that can give you a specific fraction of the source voltage.
So like splitting the voltage up.
You got it. Typically, they involve 2 or more resistors in series. By carefully choosing the values of those resistors, you can control the output voltage precisely.
Okay, that's pretty clever. And what about making the output voltage adjustable? Like if you need different voltages for different devices?
That's where variable resistors come in handy. You can use them in a potential divider to create an adjustable output voltage. That's how many devices can adapt to different power sources or adjust their brightness or volume.
So it's like a volume knob for electricity.
Yeah.
I never thought of it that way. Could you even use a potential divider with a sensor to create a circuit that reacts to its environment?
Absolutely. Imagine a light sensor connected to a potential divider. As the light level changes, the resistance of the sensor changes, which in turn changes the output voltage.
Oh, I see. And that change in voltage could then trigger something else, like turning on a light when it gets dark.
Exactly. Potential dividers are incredibly versatile, and they're used in all sorts of applications, from sensor circuits to audio equipment.
That's amazing. So we can split voltage, adjust voltage, even make it react to the environment. It's like we're becoming electrical engineers.
Yeah.
But before we get too carried away, let's go back to the battery for a minute. Why do they eventually run out of power? What's this internal resistance all about?
Ah, great question. Internal resistance is a key concept when understanding real-world batteries. See, unlike those perfect batteries we see in textbooks, real batteries have some resistance inside them.
So it's like the battery's fighting against itself a little bit, trying to push charge out, but also resisting that flow.
That's a good way to think about it. And this internal resistance means that the actual voltage you get from a battery, what we call the terminal potential difference, is a bit lower than the battery's ideal voltage or electromotive force, EMF.
Okay, so EMS is like the battery's full potential, and internal resistance is kind of stealing some of that energy away.
You got it. And as a battery discharges, its internal resistance tends to increase, which means more energy is lost within the battery itself.
That explains why batteries seem to get weaker over time. But how do we actually measure a battery's EMF? Wouldn't that internal resistance mess up the reading?
That's a good point. To get an accurate EMF measurement, we measure the voltage across the battery when there's no current flowing through it.
Right.
That way, there's no voltage drop across the internal resistance.
So we're basically tricking the battery into showing us its true potential.
Exactly. It's a bit like measuring its voltage when it's resting. We've covered a lot of ground today, haven't we? From basic concepts like current and voltage to more complex ideas like potential dividers and internal resistance. It's amazing how all these pieces fit together to create the world of electricity.
I feel like my brain is buzzing with all these electrical concepts now. It's amazing how much we've uncovered in just one deep dive.
It is pretty remarkable, isn't it? We started with those fundamental ideas like current, voltage, and resistance. Then we explored how different components like resistors, diodes, and filament lamps behave in circuits.
Right. And who could forget those mind-bending concepts like resistivity, thermistors, and superconductors?
It's a lot to take in. But the important thing is that these concepts aren't just theoretical. They're the building blocks of the technology that surrounds us every single day.
Okay, so we've got the knowledge, but why should I care? I mean, I'm not planning on becoming an electrical engineer.
Fair enough. But understanding these basic principles empowers you as a consumer and as a citizen.
Empowers me how?
Well, for one thing, it helps you make more informed decisions about the technology you use. You can choose more energy-efficient appliances, troubleshoot simple electrical problems around the house, even understand the debates around renewable energy and power grids.
Oh, I see what you mean. It's not just about passing physics exams. It's about understanding the world around us better.
Exactly. And it's about appreciating the incredible ingenuity behind the electrical systems that make our modern lives possible.
Yeah, I have to admit, I've gained a whole new level of respect for the people who design and build all this stuff. It's not magic, it's science. And now I kind of understand a bit of that science.
That's the beauty of learning, isn't it? It demystifies the world around us. And remember, we've only scratched the surface of electricity here. There's a whole universe of fascinating topics out there.
Oh, I believe it. Like those semiconductors you mentioned earlier. Those are what make all our computers and smartphones work, right?
Right. Semiconductors are the backbone of modern electronics. And then there's the ongoing research into superconductors and their potential to revolutionize energy transmission. And let's not forget about all the amazing applications of potential dividers in sensor circuits and beyond.
It sounds like there's always more to learn. But that's a good thing, right? It keeps things interesting.
Absolutely. And that's what we encourage everyone to do. Stay curious, keep asking questions, and never stop exploring.
Great advice. Well, thanks for guiding us through this electrifying journey. I feel like I finally grasped some of those key concepts from A-level physics and even learned some new things along the way.
It was my pleasure. Remember, curiosity is the spark that ignites understanding. Keep that spark alive, and you'll continue to discover amazing things about the world around you.
To all our listeners, we hope you enjoyed this deep dive into the world of electricity. And until next time, stay curious.